Alrighty, y'all. Today I'm looking at question 1 and question 4 for homework number 2. So first one, we're trying to find the charge density on a sheet given the flux through the square. So we know that flux, our definition of flux, is the electric field dotted with this area vector, right? And what that's just going to be is the magnitude of that electric field times the magnitude of that area vector, which is just the area, times cosine of the angle in between them, right? So for this, we have our square up here, and the area vector, it's given right here, is parallel to E, because our electric field's coming this way, and our area vector is going that way. So since they're parallel, the angle between is going to be 0, cosine of 0 is just going to be 1. So that's just going to disappear, right? So now we can have that our flux is equal to the magnitude of our electric field times the magnitude of our area. So we're given the flux in the problem, and we're also given the side length of the square, so we can calculate the area. So our area is just going to be 5 centimeters is 0.05 meters squared. And that's going to be, we set that with our flux, 3 times 10 to the negative 5th equals our electric field times this 0.05 squared. So if we can find then we find our electric field is equal to 3 times 10 to the negative 5 over 0.05 squared, right? But this, near a large charged sheet, if we estimate that as an infinite plane, like we have before, we have an equation to find the electric field for an infinite plane. That's going to be our sigma over 2 epsilon naught, right? So we have our electric field over here. We have our electric field over here. So we're going to set them equal now. So we're going to 3 times 10 to the negative 5th over 0.05 squared. It's going to be equal to our sigma over 2 epsilon naught. Now we just multiply both sides by this 2 epsilon naught, and we're going to isolate that sigma. So we get sigma equals 3 times 10 to the negative 5th times 2 epsilon naught all over 0.05 squared. If you multiply that out, that's going to get you your answer for that sigma. And of course, if we plug in, we're plugging in epsilon naught equals 8.85 times 10 to the negative 12th. I can rewrite that neater. 8.85 times 10 to the negative 12th. And that's going to give you your answer for sigma for question 1. Now if we look at question 4, we have the surface charge density on a long straight metallic pipe is sigma. So we have our metallic pipe here. And the electric field outside the pipe, a distance r from the axis. That's what we're trying to find the field. We have a diameter of the pipe given as 2a. Right? So if we're trying to find a radius from the surface, or from the axis, what that's going to be, we're going to use cylindrical symmetry to build a Gaussian surface around this that's cylindrical. So if you have our cylindrical surface, then we can use our cylindrical symmetry equation. In this symmetry equation, we have that our V equals the electric field times 2 pi RL, because again, that's just our equation for flux, is our electric field times the area that it's going through, and that's for our cylindrical symmetry. And then we also have, obviously, because it's a Gaussian surface, we have the Q enclosed over epsilon naught, right? So we can set these equal, but we still have to find out what this Q enclosed is, right? So normally the Q enclosed would just be lambda times L, but we don't have a lambda, we don't have a length per unit, we don't have a charge per unit length, we have a charge per sigma, we have the charge per area. So now our Q enclosed is going to have to be this sigma times the surface area of this metal pipe, our surface area there. And the ends are open, so we're just going to do it's just the outside surface area. So that's going to be our 2 pi r times L, but we have our r because our 2a is the diameter, so that means that 2 times the diameter, a is going to equal our r. So we can replace this with our 2 pi a times L. That's going to be our Q enclosed. Now if we set these equal, we get the electric field times 2 pi RL, and this is the R that we're looking at from the center, is equal to sigma 2 pi AL over epsilon naught. Now obviously 2 pi and the L are all going to cancel, so we're left with electric field times R is equal to sigma times A over epsilon naught. And then from there we just divide by R, and we get that our electric field is going to be equal to the sigma times A over epsilon naught R. That's going to be your answer for question 4. All right, well, thank you very much for watching. I hope you found this at least a little bit helpful. Let me know if you have any more questions about this or any other problems that you want to walk through for, and I will do my best to explain them because I guess Sydney explains stuff.